Ralph, air to water is the way to go. It's the only sensible approach to where we're going today's energy changes.
Are you serious, Tim? Air to air has been out forever. It's proven. And oh, we have company.
Oh, well, good morning.
Good morning. My name is Ralph Gates with Emerson Swan.
Hi, I'm Tim Simpson. I'm also with Emerson Swan.
So this morning we're going to talk about air to air and air to water technology and how they're similar and how they're different. I think, Tim, basically, at the end of the day, we know we've been in this for a while. We know every application is different, don't we?
We sure do. We've been doing this for a long time. Ralph, with air to water, it's a much more traditional approach we're going to do in hydraulics inside the home or the business, whichever way it's going to be. And it's just another alternative to today's energy needs to be carbon free and things like that. And then obviously with air to air, it's a very tried and true approach. It's something we understand very well.
At the core, they're very similar.
Yeah, they are very similar. Some of the differences with air to water is we're using a monoblock type system where everything is self-contained.
So monoblock, can you explain that?
Yeah, that's a great question. Thanks, Ralph. So with a monoblock type system, the refrigerant system is completely self-contained within the unit outside. We don't need to bring refrigerant into the home. We don't need to concern ourselves with refrigerant systems whatsoever. We simply have two water connections. We have a power connection and then obviously a control connection. And from there, we just bring the water inside the house.
So that's somewhat different than the traditional air-to-air that we see in ductless mini splits, where we're bringing the refrigerant lines directly into the house to each room, and so that's interesting. Nothing enters the home other than the water itself, if you will.
Our systems are both low temperature type systems. I mean, obviously with air type systems, you can go down much lower than we can with air to water, and there's good reason for that. And it's all to do with the refrigerant cycle and the mechanical components and the way that we transfer energy. So we both understand that. But when it comes to heat pump technology, it's a little bit of an unknown. And
it's a mystery, isn't it?
Yeah, it really is. Quite often I try to relate to a refrigerator. With a refrigerator, we're not putting cold energy in.
We're not?
No.
Oh, really?
No, we're removing the heat that's within it. Even in a freezer, which is operating at 0 or 2 degrees, we're still removing heat from that, and we're just transferring that from one source to the other.
So we get that question a lot on a lot of the training that Emerson Swan does within the industry, and I find it fascinating that there's not a really good understanding by a lot of contractors out there on actually how it works, but yet it's so basic and so simple.
Yeah, it really is.
So to your point, a refrigerator, we're taking the heat out of the inside of that box, right? And we're dumping it to the rear of the refrigerator, and voila, that's how we have warm air rises out of the back of the refrigerator. It's all that warm air that came out of the box. Well, when you look at air conditioning, it's really not all that different. In fact, it's the same, right? We're taking warm air out of the home and we're expelling it to the outdoor unit. I often say that, it could be 95 degrees outside and you go buy an upblast outdoor condensing unit and it's almost human nature. You have to put your hand over the top, right, to feel that air.
We all do.
Right? And it's hotter than the ambient air temperature outside. So where does that heat come from?
Yeah. That's all the rejected energy that's within the home.
Pretty simple, isn't it?
Yeah, it's very simple.
Yeah.
And in reverse, when we go to heat pump mode, we're simply doing just the opposite. We're gathering all of the energy that's atmospheric and taking that warm energy through the refrigerant cycle and putting it inside the home.
So we're changing the direction of the refrigerant?
Yeah, we are.
But not technically, but we're doing it through a device called a
reversing valve.
A reversing valve, right.
Yeah. It's there's no real magic to any of this. We've had heat pumps since the early 80s. It's really the new technology that's made them different today than what they were then.
Absolutely. Remember back in the day when heat pumps were only good down to like 30 degree above zero? Boy, the technology has changed. And the concept stays the same to this day. We're grabbing heat out of the outside air. So I often get the the question during my training classes was, how exactly does that work?
Yeah. Yeah, today's technology has come such a long ways. Vapor injection compressors, micro channel coils, larger coils. All of these things contribute to why we can get to these low temperatures. And to your point, yeah, you can get down to 90 and negative 31. With water to air to water heat pumps, at about -4 is about where we tap out. We can go a little bit lower, but that's about where we tap out right there. However, we can do domestic hot water with ours. We can do heating. We can do cooling all out of this same system. And, that leads to needing a secondary energy source with ours where you don't need it. But, in a lot of retrofit situations, that secondary energy source could be the existing boiler or anything like that.
If you have an existing heating system in a home and it's a good operational order, perhaps you want to put an air-to-air system in that might meet partial load of the home. And the only problem is the two systems don't know each other exist. So what we're finding over the past number of years is integrated controllers have come into play to the point where the system's actually able to control which system is the best to apply into that home depending upon the outdoor air temperature.
Yeah, that's huge today. Controls play a major role in how these systems work. Without controls, we just wouldn't be able to do what we do today, regardless of manufacturer. It's very important to know what system is operating, whether it's operating efficiently,
Correct.
and what your ambient conditions are like outside, whether you've gone into defrost. There's a host of reasons to have sophisticated controls today that just didn't exist 5 years ago.
Absolutely. So Tim, if you're going to look at each of our systems, the basic core is the same. We both use a refrigeration cycle, don't we?
We do, yeah.
So I can tell you on the air-to-air, on the heat pump side, we're attracting energy or heat from the outside. We're delivering it to the inside. We are delivering to the inside via line sets. So the refrigerant, I should say, is entering the home into one of my emitters.
Yeah, our emitters actually look very much the same. When we transfer energy, we're doing it very much similar to you, but with us, we actually have the heat exchanger within the unit. So we're going from refrigerant to water right there within the unit. And our transfer of energy is hydronic from that point forward. And again, our emitters, your emitters, if you were looking at an emitter on the wall and you didn't know what was outside, you probably wouldn't know whether it's air to water or air to air.
You're absolutely right. You look at my emitters. I have high wall units. I have ducted units. I have a whole array of indoor emitters, and you have the same.
As well, Ralph. We have the high wall, we have the ducted units, we have the ceiling cassettes, very much like yours. The transfer of energy from the emitters into the room, into a residential setting, it's very much the same. It's just the way in which we get the energy from the outdoor unit to the inside of the home.
So your distribution system is very similar to hydronic heating systems that have been around for decades and decades.
Yeah, they are. With our hydronic system, often we keep the existing boiler as secondary energy. The controls, as we talked about earlier, the controls on board know when to use the existing boiler, and they know when to use an air-to-water heat pump. It's all on what is most advantageous based on the ambient conditions as well as the home's conditions. Maybe now's a good time to look at a systematic drawing of what an air-to-water heat pump would look like.
Drawings always work for me.
Yeah, great. So, when we ever do an air-to-water system, you're looking at that drawing now. We always start with the outdoor unit. The outdoor unit is connected through some traditional piping. It will be 1.25 inch and a half piping. And it always feeds into a buffer tank. And the reason for the buffer tank is twofold. One, it's an energy separation. We always want to separate the energy from the inside of the home to the outside. Secondly, we need the buffer tank for flows of the unit. And the flows of the unit are very important so we don't short cycle the compressor. And in relationship to the buffer tank, this is one of those situations where bigger is better because it is the flywheel of the system. So when you have a micro zone, why would you want to run the outdoor unit? Why wouldn't you pull the energy off from the buffer tank first?
Makes
That
sense.
sort of makes sense?
Makes absolute sense.
Yeah, so coming out of the buffer tank, we traditionally do a variable speed pump, a pressure dependent variable speed pump. It does its thing all on its own, and then we feed to our emitters. Our emitters are low temperature emitters. Even though the units are capable of up to 140 degrees of hot water and down to 40 degrees of chilled water, we always do low temperature emitters. Let me show you a second slide with the secondary energy actually built into the system. We do that simply through a closely spaced T. And the controls are the magic to everything. That's the controls control secondary energy. They control what operates when, and it's all based on ambient conditions, loop conditions, and the house's conditions.
So Tim, low temperature emitters. When I think about that statement on your air to water equipment, that's really what we're doing on the air to air as well.
Yeah.
On the heat pump side, I'm looking for a 40-degree temperature rise.
Which would give you what for a discharge temperature on a perfect day?
110, 115 degrees.
And that's just about where we are as well.
Imagine that.
Yeah, imagine. Hey,
So I guess we do have something in
we
common.
do. Yeah.
How do you go about sizing this equipment? I know back in the day when we started, right, it was 3 fingers was a 3-section cast iron boiler. Is that still the way we do it?
Yeah, in my old days, it was 3 fingers with 3 tons.
So Tim, a big part of our training in regards to design and layout is, first of all, understand the application. So where on your system, you're typically dealing with a whole house approach, right?
We are, often.
Right? Now you're zoning it and whatnot, but with the air to air, I can condition a portion of the house. I can condition the entire house. And in doing that, I can also take advantage of the secondary heating system in the home.
Yeah.
So when I do any of these, first of all, I want to do a heat loss, heat gain on it, correct?
So important.
It really is.
The manual J.
Manual J on it. So I know exactly what's going on in each room. So if I want to do what I call a spot application, where maybe I'm doing the common living areas, I know exactly what to put into that space at whatever design outdoor air temperature I'm looking for. Now, if I'm doing the entire home, I do the same thing. I look at the existing heating system, determine if it's something that we could possibly use as a backup source. Then I'm doing my manual J again on whatever outdoor air temperature I'm looking at to look at the balance point, to where I want to engage that backup heating system.
Ralph, you talked about balance point. Tell me, what do you actually mean by balance point?
So balance point is interesting. So let me lay this one on you. You ever heard of this before? As the outdoor air temperature gets colder, the heat loss of a structure increases.
Of course it does.
Imagine that.
Yeah.
Now, compare that to a heat pump. In a heat pump, depending upon the model and the ratings of the heat pump, we have different types of units that are rated at different outdoor air temperatures.
Some go lower than others.
Absolutely. So on a heat pump, as the temperature outside decreases, so doesn't the output of the heat pump.
The D rate.
The D rate, exactly.
I've heard of this.
Yes, the old D rate. So we need to know that balance point. So in this slide that's up on the screen, you're going to see a green shaded area indicated by supplemental heat. So below that balance point is where I'm going to need an additional heat source to supply enough heat to make that home comfortable.
So let me ask Ralph. So when we reach that balance point, when we've designed to that balance point that you talked about, if it was at 20 degrees, say, would you actually shut your system off, or would you allow your system to continue to supplement the secondary energy?
I think it all depends on what type of system you're selecting. So if my unit, if my air-to-air unit is still energy efficient below that balance point, I'm going to use it along with my supplemental heat. It's all about the capabilities of each of the units and the application I'm designing to. Because there's another thing we talk about, and it has actually to do with an economic balance point, right?
The cost of fuel.
The cost of fuel. At what point does my cost of electricity go beyond the cost of my secondary heat source. So Tim, we live in the Northeast.
Yeah.
So what could that secondary heat source be?
Well, that secondary source could be gas. Gas is a very common secondary heat source. Oil could be a good secondary heat source. Those are two of the more predominant secondary energy sources right there.
Absolutely. So we need to know the cost of each.
Yeah. So with oil, it's fluctuating, and with gas, it's a lot more stable. So we can very quickly develop a secondary energy graph to know when to shut off your energy source or my energy source as supplemental.
And let's not forget, in the Northeast, we still have a lot of homes that are heated by electric resistance baseboard.
Yeah, that was a big movement back in the 70s. A lot of electric baseboard, electric ceilings, electric wall panels, and even electric boilers as standalone devices. So to your point, Ralph, absolutely, and we know one thing for sure, that whichever energy source you go with, be it air to air or air to water, it's a lot more efficient than just an electric system.
Huge opportunities for both of us.
Oh, absolutely.
Most people have seen an air to air. What's an air to water system look like?
Well, Ralph, thank you very much. You know, an air to water system, the condensers outside, look very traditional to your condensers or anyone else's condensers as far as that go. But with an air to water system, they can be a little more sophisticated depending on the house, the design, things like that. We have a lot of homes that is using strictly a single air to water heat pump. And then we have homes that are using up to 6 air to water heat pumps. If you're looking at this slide that's up there right now, this 6,000 square foot home actually uses 6 air to water heat pumps. It's not well insulated, it's older, and there's good reasoning to use that many heat pumps in this particular home. It also has a 300-foot run from the heat pumps all the way to the house. And then we have other heat pumps. There's one in New Hampshire recently. It's 6,000 square feet as well. It's highly insulated, very well engineered, and it's only using 1 air to water heat pump. It's pretty interesting on just how important it is to have good insulation and a good design.
So one thing comes to mind though. You got water in those pipes.
Yeah.
And you just said it's going 300 feet underground into the home, which is spectacular because now you can get the condensing unit away from the home for obvious reasons. But how do you handle that whole freezing thing?
Yeah, great question. You know, we obviously have to glycol the system. There's no two ways about it. And once we get into the home, a decision needs to be made. Do you want to run glycol in the home, or do you want to stop at a heat exchanger? Mm-hmm. And if we stop at the heat exchanger, we've completely separated the glycol to basically outside of the home. And if we don't, then we have glycol throughout the home. So there's reasons to do it each way. But that's the method that we have to do that, because otherwise we would suffer with a freeze up.
So the deal with the glycol, that's really no different than how we've been doing it over the years.
Yeah, for a lot of years.
Right? So do we separate it before it comes into the home, or do we use it throughout the home? So that's really nothing new. We've been dealing with that forever.
Yeah.
Now, one of the other things I noticed was your buffer tank. That buffer tank's outside.
Good point. So when we're dealing with an existing home, because these buffer tanks can get relatively large, we can't always put them inside the home. Sometimes there just isn't space enough. Or perhaps the basement is finished and we just can't put it beside the boiler, whatever those reasons are. So putting it outside is absolutely an option. Today's buffer tanks, they're so well insulated, we're losing about 1 degree per hour
Really?
in transmitted loss. So not a lot of energy loss with putting a buffer tank outside today. However, aesthetically, it's not always the correct approach to put the buffer tank outside. Not everybody wants to look at it. So it all depends, based on situation to situation, home to home, how we design and put the system together.
But at the end of the day, we have options.
We have options, and we have the experience to bring you those options. And that's what Emerson Swan's all about.
Absolutely.
Ralph, this whole air to water system might seem a little mysterious, but really it's very basic. And we actually have a home builder in New Hampshire, a very high-end home builder. They built homes to R60 walls, real low energy type usage. And they ship around the world, and the only product that they recommend and ship with is our air to water units. And um, we have this down to a system now where we have all of the emitters included with the home, the outdoor units included with the home, the secondary energy sources included with the home, and it literally is all packaged and shipped. It's amazing because some of these bedrooms are only requiring 2 and 3,000 BTUs of heat.
So we've basically been talking about air to air and air to water systems so far. You know, on my side, I'm starting out at 3/4 of a ton for that spot heating application. All the way up to basically 4 tons. On the ductless mini split side, we have air to air systems that can go much larger and do much larger buildings. So I'm sure on the air to water side, you don't drop off at 4 tons, do you?
Yeah, we actually drop at 4 tons residentially. So while we drop off at 4 tons residentially, you just got to keep in mind that we can put multiple units together, up to 6 with controls, to make up to a 27-ton plant residentially. So we vary everywhere from 1.7 tons up to 27 tons residentially, single phase. But commercially, we go all the way up to 960 tons with a single unit.
It's a big building.
Yeah. To kind of bring that full circle, just this week we're finishing up on a project. It's up in northern Vermont. It's a very world-recognized academy, and this is a new build. It's a $20 million new build for this particular academy, and the reason they did is they want to be considered fossil-free and carbon-free for this new build. It's the direction of this academy. It's very interesting.
So Tim, that's what it's all about, carbon reduction, right?
It is. Yeah, carbon reduction, the whole going green movement is a very forward, fast-paced movement. It's growing in popularity faster in the Northeast, perhaps, than it is in some other states. But because we are heating predominant, it is so important to look at alternative energy sources that get you to being carbon-free.
So Tim, if you look at the incentives in Massachusetts, they're really outstanding.
They are.
Up to $1,250 per ton
Per ton.
for air to air and also air to water
Exactly.
when
Yep.
when you're displacing a fossil fuel.
Yes, exactly. Yeah, as long as you're displacing a fossil fuel, if you don't have an electric-based system today, you can gain that $1,250 per ton incentive in Massachusetts.
So what happens if you have an existing electric system?
Yeah, there's actually a bucket of incentives for just that as well. It's different than when you're basing it on a fossil fuel system, but if you have an electric system, we can steer you in that right direction to get those incentives as well.
So Tim, we're not all that different after all, are we?
Not really. We really aren't. We're all based on a refrigerant system with mechanical components, and how we transfer the energy, that's where we differ. Your system is more tried and true, more accepted here in the US. In Europe, we've been accepted for years with air to water, and it's only been the last 10 or 12 years that air to water has been introduced in the States. So with all that said, really, we are the experts when it comes to air to water or air to air systems. And if you need support, we are here to help you. If you need training, reach out to Emerson Swan.
I couldn't have said it better. I want to thank you for this time. I totally enjoyed this conversation.
As well, Ralph,
You have an awesome day.
as well.